Okay, shall we start? All right. 10 past 4. Okay, assalamualaikum and very good evening to all of you. So we have come to the week 11. Week 13, and next week will be the final week, the last final week, week 14, and then we're going to have 1 week for final revision before we have our test, final examination, final assessment on the 31st July. Okay, so the last topic is actually on the switch mode inverter. Uh, the switch mode inverter is actually the opposite to the AC DC rectifier. Okay, so in power electronic, what do we have is basically we're going to have AC or DC at the input, and this is our converter. All right, second. Okay, and then we have the AC or DC, and then we have our converter, and the output can be either DC or AC. So we have looked into the conversion of AC to DC. We also look into AC to AC, and we also have looked into DC to DC. The final um, or the last topology or circuit is of course the DC to DC. DC to AC. So this is the opposite to the rectifier, and this is known as inverter. Switch mode because we switch the input. All right. So input is always a constant DC voltage. A constant DC voltage is a perfect DC voltage waveform. So how to change and to make it an AC waveform is just by using a switch mode converter, right? So which means we're going to switch at any instant, okay, so that we can shift, or we want to make it the AC, the output waveform, which is periodical waveform. Should be a periodical waveform or repeating waveform. Yeah, our target is to have a repeating output waveforms whereby it has a frequency of operations. We have the repeating waveform, output waveform with a certain frequency. So when you talk about AC, the perfect waveform is always an AC sinusoidal signal waveform. This is the most beautiful, the most perfect AC waveform, isn't it? So we know that with this sinusoidal waveform, we could have a one period from there to there, and we have one period t equals to 1 over f, isn't it? So that's it. We want to have a DC input and the output is AC. So in terms of applications, this is mostly used for the solar PV system, isn't it? We have a solar, which is the output of the solar panel is always in the form of DC waveform, DC current, DC voltage, and to suit the AC load, for example, your heater, and you want to light up the house, you need an AC voltage or AC system, isn't it? So you need to have this inverter so that your DC voltage will be converted into an AC waveform. Okay, so right, so we talk about I'm just going to give a review, the introduction, give you a overview of what you're going to learn in the video. Okay, I've already shared with you the video just to give you an overview what you're going to watch or learn in that particular video. It's a 1 hour, 1+ hour video, and it talks about the inverter. So you need to think of the input is a DC, a straight constant input, and the output, our target. And the target is to get a perfect sinusoidal AC waveform, but normally, but if we could have any waveform which is repeating, we have for example, a square waveform, isn't it? Square waveform is also a repeating waveform. This is enough for the output, right? To have a square waveform at the output, and therefore this is already an AC waveform. Okay, this is already AC waveform. Or you could have a quasi square waveform, isn't it? Quasi, it will be in that particular waveform. This is a quasi square waveform, isn't it? Okay, quasi square waveform. Okay, so that's enough. Once we have this AC repetitive waveform, the AC can appreciate that, and it will see it as a AC voltage, and the load can is enough for it to function. Right. So therefore, you look at the and when we talk about AC output, there must be, or the category could be single phase inverter, right? And the output also can be a three phase inverter. That's it. Single phase inverter, and the input is always a constant DC voltage. Right. So the single phase inverter could generate three types of output waveform. For the single phase waveform inverter, we're going to look into, okay, when we talk about topology, in terms of topology, let me show you. Okay, in terms of topology or the circuit, right? So that could be input, and then you're going to connect to a switch directly to that particular. This is known as leg, right? This is first leg, leg, first leg, and then that will be connected to another leg. And at the center here we have the resistor or the load. Okay, this is the load. Okay, this is the circuit that we're going to discuss. Okay, so we talk about half wave or half bridge topology. The first leg consists of switch, and the second leg here will consist of capacitor. So this is known as half bridge topology, which means we only use half of the bridge. This is the bridge that we'll talk about. We have a bridge here, so half of the bridge is we use the active switches, right? Two switches here, and this is replaced by a capacitor. Okay, and when we talk about full bridge, all components here are switches, right? So when we use all switches here, this is also a switch, then this is known as full bridge topology. Okay, single phase because the output only have a one phase only. Okay, only one phase at the output. Right. So later on we're going to look at the three phase. How are we going to generate three phase? Okay, so this is topology, right? Half bridge or full bridge, and the techniques will be different. The technique to control the switching, we call it control signals or control technique. will be classified or categorized into three categories. 1, 2, 3. So the method to control the switching here can be, the first one will be a square waveform, and then we're going to have a quasi-square waveform, and finally the other technique will be the PWM, pulse width modulation technique. So there are three techniques, three control strategy to control the switches here. So this is the control technique, and this is the bridge, is the topology, the circuit. The circuit is always either half bridge or full bridge, but the output, the control technique can be a square, quasi, or PWM waveform. Right? So this is single phase inverter. What about the three phase? So for three phase, we're going to discuss on, we're going to have one input, which is always a DC waveform, and that will be connected to 1, 2, 3 legs. Okay, so we're going to connect that. This will be connected to there, that, that, and the output will be connected to one resistor, first resistor, second resistor, and finally the third resistor load. And this is the load, and that will be the neutral point. Okay, so with this arrangement, we're going to get a three-phase output or three-phase inverter. So that will be phase 1, phase 2, phase 3. Phase 1, phase 2, phase 3. And to control the switches, there are 120 to 120 conduction mode. The other one is 180-degree conduction mode, and finally the sinusoidal PWM. Right? So it is the same. The circuit is only one circuit that needs to be considered, which is different to the single phase, because single phase can be full bridge or half bridge, isn't it? Half bridge or full bridge. But for the three phase inverter, you're only going to learn on the one single circuit, the three phase active inverter here. So you have 6 switches here, and then the center of the leg will be connected to the output resistor. So now we have one phase, phase 2, phase 3. So we have 3 phases, and of course there will be a slight phase shift between each other, because we need to maintain that phasor diagram, isn't it? Red, and we have yellow, and the other one would be the blue. Okay, it is always red, yellow, blue phasor diagram. Okay, any questions? Okay, so I'm just going to give you an overview. The rest on the detail on the circuits will be discussed in the video. Okay, right. So, alright. So this is single phase inverter. Tengok mungkin probably a few of you have watched the video. So this is the first half bridge topology. Okay, so how the circuit works? Okay, let's look at the first circuit here, square waveform. So to be able to get the square waveform, you're going to switch one here with a pulse of 50 degree, 50% here, 50% there. 50% on, and the other one will be, the other 50% will be off. Is it on? And then this is off for the switches here. Alright? So therefore, look at the waveform here. So let's consider, okay, let's look at this particular waveform. And this is a waveform signal to the switch 1. Yeah. So remember, you have a DC input, and then you have just now we have a capacitor here, isn't it? No problem. You can have a capacitor on the left hand side or right hand side. This considered as a very large capacitor because we want a constant output voltage, and we have so we need to have a very large capacitor there. And this is your switch, this is your switch 2. Okay, so this is, and at the center here you have a resistor. And we're going to analyze one by one. First, we have considered to understand the circuit, just put in a resistor, then we look at this switch. So this is switch 1 and this is switch 2, and these two, okay, so these two signals will be fed to switch 1 and switch 2. So whenever switch 1 on, switch 2 must off. Okay, must of switch 1 on, switch 2 off. So in practical, there will be some delay here. We don't want to be both switch turn on at the same time. Why? Because that will result in a short circuit, isn't it? So if you could think of this, you switch 1 and switch 2 simultaneously, and therefore this is short circuit, switch on short circuit, switch 2 short circuit because it is turned on, and therefore we can see that the whole area here will be this short, therefore that area will be short circuit 0. So a very large current will flow and damage the switches there. So we need to avoid that situation. In practical, we're going to have some delay between switch 1, so which means we're going to have that switch 1, that, okay, then you have a normal, okay. So there is no overlap of switching. Okay, so in practical, but normally in the theory we just show this, and we understood that switch 1 switch 2 cannot be turned on at the same time. So whenever switch 1 is on, switch 2 is off, and the angle is always 0, 180 degree, this is 360 degree. So when the switch 1 on, the switch 2 off, and when switch 1 off, switch 2 is on. So when switch 1 is on in this particular area here, okay, in this particular area here, we know that switch 1 is on. So this is your input, and then this is a big capacitor, if you can refer to your note, right? So this is the big capacitor, and only we have switch 1, and this is switch 2. Okay, and we have a resistor at the center here. Right, let's say switch 1 is on. So during this time, okay, switch 1 is on, isn't it? So the current will flow from here okay, there to there, and definitely go to there, and it will follow. Sorry. Switch 1 is on, isn't it? Okay, switch 1 is on, so it will flow through resistor here, come back to this capacitor. Okay, so this is when switch 1 is on. So if you look carefully, because we have a very large capacitor here, let's say this is 100 volt, and the input is 100 volt. Since we have a very large capacitor, what happens is that will be receiving only half of the voltage here and the other half on the bottom group. So we have these two player. We have two sorry, wait, 50. So let me draw again. So this is 100 volt capacitor, again. This is your switch 1, switch 2, back to that. Okay, just look at this, focus on this input and capacitor here. So we have 100 volt there, and therefore across that will be 50 volt, and there is another 50 volt. Because it's a capacitor, so it will store a 50 volt voltage there, and the other one on the bottom side will be 50 volt. Plus minus, this will be plus minus. Okay, and this is your output, isn't it? Load V out. This is plus, this is minus. Resistor that represent the load. Okay, so the current will flow through there, close to that. Switch 1 is on, so you go to that, and it will flow through R because this is off, isn't it? And it will flow through here. Come back to the okay. So when you look at the output, which is the voltage across R, what if I can rearrange that? Now I'm going to have plus minus 100 volt. Okay, I'm going to stretch that. So that will be your S1. And then you have this R. And then you have this 50 volt, plus minus. And whenever switch 1 is on, it appears as a short circuit. So this is only actually a short circuit here. So the current flow through there, across the resistor, across the capacitor, and come back here. So if you look at this point, from that point, eyes. So if you look from this point, you're going to see that 50 volt is there. So you have another 50 volt there. Voltage drop across that. So if you look closely, the output now, remember we have the 100 volt at the input. So V load now becomes 50 volt there. 50 volt across that. And whenever switch, the bottom switch is on, then we can have a minus 50 volt. You can try that. Okay, so therefore, if you look at the output, this is a square wave form, isn't it? square waveform, we know if you perform a fast Fourier analysis, okay, Fourier analysis, we're going to see the fundamental 50 Hertz. You still remember that? Yeah, 50 Hertz. Next is 150 Hertz, which is the third harmonic. This is the first harmonic, third harmonic. Then we have three fifth harmonics, which is at 5 multiplied by 50 is 250 Hertz. Then we have seventh harmonic and odd numbers. 3, 5, 3, 5, 7, 9. Okay, all the that fundamental, third harmonic, fifth harmonic, seventh harmonic, and the rest. Okay, so this is a square waveform, isn't it? But if you can think of, if we get rid of this, okay, so this is actually the harmonic spectrum of a square waveform, isn't it? This is square waveform. So if you look at the harmonic spectrum, you're going to see this, which tells you that this square waveform actually come from the fundamental 50 Hertz with certain amplitude here, which is V1 peak, and then it will add the third harmonics, then become another one, which is third harmonic. So let's see, we can divide it into 3. Okay, so with certain value of V3 peak and fifth harmonics. So you're going to see that this square waveform actually is made from the sinusoidal signal waveform at different amplitude at different frequency. Is it? Third, fifth harmonic. So my question is, if you can get rid of that, if we can have a filter that filter this out, okay, we filter this, filter that, and the rest ada lagi ni. Yeah. So what happened to the square waveform there? It left with only fundamental harmonic, isn't it? The fundamental frequency component, which is a sinusoidal voltage. So this is a perfect AC waveform already. Remember, the input is DC, the output is AC. By means of you get rid of this, you remove this, you use a filter, a specific filter, then you can get rid of all this, and then what you have is only a fundamental component. Okay, so AC is an AC waveform. Okay, so that is a square waveform. Then we proceed with a quasi-square waveform. So how to switch to have a quasi-square waveform across the resistor is by means of using or we modify a bit your switch 1 and switch 2, the control signal to switch 1 and switch 2. So what happened here, we're going to start with 0, and then after 30 degree, going to switch is on. Alright, you give a pulse here 30 and until 150 degree, because the length is always 120. Right, 30, 150, and this is 30 degree again, so that will be 180 degree, and this will be 210 degree, and here you have 120, 330 degree. Okay, therefore here you have 360 degree. Okay, so you control the switches, and you give this pulse to switch 1 and switch 2, and finally you get to see that the output consists of this waveform. Okay, you have 30 degree here, and then this is half 50 volt, then you have this 150 degree here, 180 degree, this is 210, and that will be 330 degree, and therefore you have a 360 degree there. So this is a complete signal, complete repeating AC signals at the output. Right, so similar to square waveform, if you look at the harmonic spectrum, you're going to see this is a fundamental, there is no third, then triplet harmonics. Okay? If it's a quasi square waveform, the triplet harmonics equals to 0. So you're not going to see the third. What else is a what is fifth, seventh, and the rest. Great. Okay, so that's why if you look at the waveform now, it becomes fundamental. There's no third harmonic. Fifth, seventh, there's no ninth harmonics. 11, 13. Of course, if you can look at the harmonic spectrum, you're going to see that one also. 13 harmonics. So the same argument, if we can remove this, so what left at the output is only the fundamental component. Eh? So we have the AC output, even though our eyes or at the beginning we see a quasi square waveform, but we know that this quasi square waveform has this harmonic spectrum. If we get rid of these 5, 7, 11 and the rest, what left is only the fundamental, which is the AC waveform, and it works at 50 Hz with a certain amplitude. Right, that's the basic. You're going to learn again more detail in the video. Right, so that's second control technique. And finally, we have this PWM, pulse width modulation signal. We have the same circuit, same switch, half bridge, but the method of how you control or you give an output of the control parameters or control signals to the switches is important. Okay, so unipolar PWM is pulse width modulation. So if you already taken the communication subject, you're going to see this pulse width modulation signals. You're going to see this pulse width modulation signal. Okay, so unipolar PWM. What is a PWM? It's a pulse width modulation. So the technique that we're going to use is the sinusoidal PWM. There are many PWM types or type of PWM. One of that is SPWM. S stand for sinusoidal PWM, pulse width modulation. Sinusoidal pulse width modulation. And if you look at here, there's a unipolar PWM. So what does it mean? Before that, what is a sinusoidal PWM? We're going to compare two signals. To generate the pulse width modulation, the signals PWM is actually the control signals to the switches. And we have half bridge, full bridge. What will be the first one? We know that this square waveform, isn't it? Square waveform, we switch turn on at 0 and we turn off at 180 degree. But for the quasi square waveform, we only give a delay of 30 degree. We turn on the switch and then we turn off again at 150 degree and the rest. Okay, so that is technique for control signals to the switches. In here you have a sinusoidal PWM and it is a unipolar. So what are those signals? That look at this. You compare the modulating signal. So this is known as right. This is known as modulating signal, and the triangular carrier signals here is known as the carrier signals. Right. So we have modulating signals and carrier signals. How to generate these the control signals is by comparing the modulating signals with the carrier signals. You're going to compare, which means if I can write here again, comparator, going to compare the sinusoidal signal with a carrier signal, high frequency carrier signal. Okay, so whenever sinusoidal or the sinusoidal signals greater than the carrier signals, it will produce a pulse of 1. Okay. So look at this waveform. If I can zoom it properly. Okay, so look at center here. So if we okay, let's focus on this point. Look at this point. So here we have V PWM is greater than the carrier signal Z from there to there. So if we trace down, there will be, you can see here. Look at that. Okay, it produced a 1, isn't it? Because carrier signal is greater than the sinusoidal signals. The carrier signals is greater than the sinusoidal signals, and that's why it give a output of 1. Okay? Output of 1. If you look closely here, it will give that pulse, very small area whereby carrier signals is greater than the modulating signal. That's why you have only that width, only that width, and then it keep on increasing. The width is got keep on increasing, and so this is the PWM waveform across your switch 1. This is will be connected to SPWM1 as switch 1, the top switch, and if you compare another the switch, the top switch, this is off. So the top switch will be off and then on again. So here if you look closely, there are two comparators, right? There are two comparators. The first one is to feed switch 1, the other one is to feed the switch 2. This is unipolar PWM. Okay, so this is unipolar PWM. There are two category or types of PWM. The first one is unipolar, the second one is bipolar. And there are two techniques: unipolar, bipolar PWM. So we will have a different arrangement of the comparator, and there's a bit of different control or signals in between unipolar and bipolar. Okay, so we look further down, and this is unipolar PWM. Okay, if you look closely, the difference between bipolar and unipolar is that for unipolar, look at the carrier signals. It only consists of positive value of carrier signals. The triangular carrier signals consist only of positive value. This is unipolar PWM. But if you deal with bipolar PWM, you're going to compare the modulating signals, the sinusoidal modulating signals here there, with a triangular carrier signals, but it has two values, positive and negative. Okay, so that is bipolar PWM. So that is bipolar PWM. Circuits remain the same. You could have a half bridge or full bridge. Okay, so today just an overview. This is summation. Then this is the summation. The control signals for the bottom group, and finally you're going to see the output, which is that one. So that will be the output for unipolar PWM. There is a different output waveform between unipolar PWM and bipolar PWM output. So you have to recognize, once you understand, you definitely you can recognize whether, or you can determine, or you will know whether it's a bipolar or unipolar PWM. So if you look at this is a unipolar PWM. Yeah, and it's always the circuit operation is always just like the square waveform or quasi square waveform. The circuit operation is always the same. Whenever switch 1 is on, the output will connect to the positive of the input voltage. If the bottom group is switch on, or the bottom switch will be on, you're going to have a negative across your output. Yeah, positive, negative. So this is the output. And again, if you look at remember, this is a square waveform, this is AC waveform. It has a fundamental frequency, and there's also a harmonics at we don't know what is the frequency is, but basically if you run your PSIM, you ought to see this, whereby this is fundamental and this is the rest of the harmonic. Rest of it. Look at that. The switching frequency is at 2 kilohertz. So the first component is close to 2 kilohertz. We have 50 hertz fundamental. So here this is the fundamental. Fundamental is depend on the frequency, the main frequency. So this is 50 hertz. So at 50 hertz, this is the fundamental, the fundamental components, V prime load or V load with a hat, and this is the harmonics. Okay, So again, if we can remove these harmonics, okay, by using a filter, okay, what left is only the 50 Hz component, just like the square wave and quasi square wave just now. But the only difference is when you operate with a large frequency, the component for your filter will be lot smaller, uh, compared to the square and quasi square waveform. Okay, so you boleh tengok balik lah, to give you an overview, 1 hour overview, and we just go back and watch again and again, simulate, right? I will share with you the simulation circuit with you. Okay, so now as PWM switches scheme with full bridge topology. So here we look in detail on the full bridge topology. Full bridge, which means there's no capacitor, all components are switches at the leg, first leg and second leg. So you look at this notes here. Unipolar. We have discussed on unipolar. So what is a bipolar? Odd and superior output achieved by even frequency ratio for unipolar PWM to bipolar. Just read that. Okay. Look at the number of comparator for unipolar PWM. Unipolar PWM here you have 2 comparator, but for the bipolar you only have 1 single comparator to do that. Okay, I'm not going to give a long overview. So and then 3-phase also straightforward. Okay, so for 3-phase inverter there are 3 techniques, which is 120-degree conduction mode. So you're going to look at how we're going to control the signals so that we have a 120-degree conduction mode. Next, we have a 180-degree conduction mode, and finally the same sinusoidal PWM, waveform. So 120-degree conduction mode. Look at the arrangement of the switching device, and it is always labeled as S1, S3, S5, S2, S4, S6. You must follow that arrangement or labeling of the device, because this is closely related to the control signals. So if you label in the wrong arrangement, when you prepare the signals, the control signals, it will match. It will match, and you may have, or you may not have the correct output voltage waveform. And so you must have S1, S3, S5, S2, S4, S6, and then you generate them. What is 120-degree conduction mode? Okay, he will explain to you. This is 120-degree conduction mode. So this is switch 1, switch 2, switch 3. So let's say you mess up with the labeling. Of course, the switching will be different, isn't it? And you mess up with the output voltage waveform, you're not going to have the actual output voltage waveform. So it must be arranged in this manner, or arrangement S1, S2, S3, S4, S5, S6, and your pulse from 0 to 120 degree, and then you shift 60 degree, another 120 degree for switch 2, and the rest. Okay, so that explains what is a 130-degree conduction mode, and that explains the 180-degree conduction mode. Right, go further, look into the PWM. So this is a PWM waveform for the pulse width modulation. Just compare the 3-phase signals with the triangular carrier signals. This is the triangular carrier signals. So you compare. Sama juga. You have this waveform, output voltage waveform. Okay, alright. So that basically what is the inverter is, and next week I'm going to have another video on the detailed analysis, and we're going to look at further detailed analysis on the pulse width modulation only. The which means the we're going to look at the PWM signals. Remember the PWM signals. Go back to the single phase. Look at that. So that is the switch 1, 2, 3, and now this is the switch 1, switch 2, 3, 4, 5, 6. 180 degree connection mode. Go back to PWM. So this is the PWM. Okay, so the last topic which will be covered in the final inshallah, talk about the detailed analysis. This is not detailed analysis. You get to look closely how to know what will be the degree, or at what degree here you switch turn on signals, and what will be that point. What will be that point? What will be that point? You can you want to look at further detail on the possible modulation. Okay, I think that's it. More or less 1 hour. For the overview of the inverter, and next week is a final week, and we're going to complete on the detailed analysis, and we're going to have another one assignment. If I'm not mistaken, we have another assignment to cover the inverter, and we try to look at how to push your coursework mark, and on the revision week we're going to have another one session, one video sessions on the preparation for the final assessment, inshallah. We look into what will be the target questions, the expected questions. Okay, any questions before we end up? And I believe probably some of you are preparing to go back, to go home, ataupun beraya dekat kampung ke apa semua kan, Zerid? Ada tak? Any questions?
None yet, sir.
Yes. So don't worry. Just watch the video, inshallah. It's very clear there. The video is 1 hour, over 1 hour, and we also have one tutorial on the inverter. Look closely. You have to sit down again and again. I always remind you to sit down and use your hand. You have a blank paper, draw back. You have to make some effort to understand powertrain. Powertrain is not an easy course subject. It's a difficult subject. It requires a very good circuit analysis, mathematics, so on and so forth. Okay. Any one last question? If not, we end up the session, and I'm going to share with you the video as a recording video later on. Tak ada?
Tak ada, sir.
No, sir.
Okay, Faiz. Okay, with that, have a long weekend. Selamat Hari Raya Aidiladha. Maaf saya batin, insyaAllah. Assalamualaikum and very good evening. Bye-bye.
Waalaikumsalam.
Thank you, sir.
Selamat Hari Raya.
Thank you, sir.
Bye.
Bye, sir.
Safe journey.
Bye, sir.
Okay.
Thank you, sir.